Lesson 2 is going to be our introduction to limits. And this one specifically talks about looking at limits graphically and numerically. So this is going to become very important. Hopefully for most of you, this will be a review. If not, though, this will be a nice launching point for you. So the idea of limits and using limit notation is that this makes the connections between algebra and geometry to calculus. Like, how do we use those things? We talked about average rate of change versus instantaneous rate of change. That is the algebraic connection. And we will also be talking geometrically how we can find areas under the curve of unusual shapes using limits. So that's where it comes in, and it's threaded all throughout all the units of calculus. It's a very important topic in calculus. So we're going to start by talking about proper limit notation and exactly what they mean. So if you're given a right-hand limit, you would recognize it because the notation would look like this. You would have the limit, and underneath the LIM, you would write as x approaches some value, and then you put a little plus sign here. And that means from the right. So verbally, this is saying the limit as x approaches C from the right. So the left-hand limit is going to look very much like this one. We're going to start out with our limit notation. Then as x approaches, we use an arrow, C. And then in the upper left, we're going to put a negative sign that indicates from the left of the function. So verbally, we're saying the limit as x approaches C again, from the right. Okay, and then finally, in general, if you're just writing the limit, you don't need to have the little plus or minus. So we just write the limit as x approaches C of f of x. So this is the limit as x approaches C. Okay, so those are the notations we're going to use from now on. Okay, so let's take a look at how we use these by looking at this rational function. We have f of x equals 3x squared minus 8x minus 3 divided by x squared minus 9. So we want to go through this and do these simple things to the function. I already gave you the graph, so we're going to factor and simplify it. So we're going to start by factoring both the top and the bottom. The top factors into 3x plus 1 times x plus 3, x minus 3. And the denominator is the difference of squares, so it factors into x plus 3 times x minus 3. So simplified, this gives us, these will cancel, 3x plus 1 over x plus 3. Okay, so what we did is right here we have a removable discontinuity. And what that does is create a hole in the graph. So the coordinates of the hole, and you can see it on the graph here, right here, are going to be at that x equals 3. So it's going to be at, instead of coordinates, I'm just going to write x equals 3. Okay. now the domain and the range. Before I write those, I want to talk about the asymptotes a little bit because they will affect the domain and range. So you can see we have one vertical asymptote. That is, that point of x is a non-removable discontinuity. Okay, and that corresponds to this part of the equation, or this part here. So our vertical asymptote occurs at x equals -3. Our horizontal asymptote occurs at this horizontal line right here, and that comes from the fact that in our simplified form, they have the same degree, so it's the ratio of the leading coefficients, 3/1. So we get y equals 3. Okay, so that's going to affect our range. Okay, and our vertical asymptote will affect our domain. So we have two discontinuities. So those have to be excluded from our domain. So writing this in interval form, we go from -infinity to our non-removable discontinuity, which is -3. And we're going to join that with going from -3 to our removable discontinuity, which is at 3. And we're going to join that with 3 to infinity. Okay, and our range, if you notice that the curve has lots of positive values and negative values that continue, but the one value it doesn't touch is at y equals 3, because that is our horizontal asymptote. So our range is going to be from -infinity to 3, and then from 3 to infinity. That's the only y value that's excluded. Okay, so how does that help us with what we're doing with limits? So that's what we're going to go for next. Okay, so going back to what we did in pre-calculus, we need to convert some of the things we talked about in terms of our asymptotes into limit notation in calculus. So it's the same graph as before. So what we're going to do is we're going to compare these two ways we thought about it before. So the first one is as x approaches -infinity, the graph of f of x. Okay, and let me bring the graph in here again. The graph of f of x, what does that approach? So what we have is we have this idea. So our x's are getting smaller and smaller this way. So the graph is approaching 3. Okay, and the same thing is happening as x approaches infinity. So now we're moving along the curve this way. We are going to be halted by our horizontal asymptote. So f of x is approaching 3 as well. Now, that's our pre-calculus notion. To write it in calculus form, we would write the limit as x approaches -infinity of f of x is 3, and the limit as x approaches positive infinity of f of x is 3. Okay, so that takes care of our horizontal asymptotes. So now we want to talk about our vertical asymptotes. So as x approaches, let me erase all this off the graph so I don't crowd it. As x approaches -3 from the right. So what that's saying is we're going to go along the curve from the right-hand side. So you can start way out here somewhere, and you trace the curve towards -3. And you look what is happening as you get to -3. And what you see is from the right-hand side, the values of the function are getting smaller and smaller. So the values of f of x are approaching negative infinity. So in calculus, we would write it this way. The limit as x approaches -3 from the left, from the right of f of x is going to equal negative infinity. So we put that little plus there to the upper left of the x value. So now, when we look at the next one, we're talking about approaching +3 from the left. So we start over here somewhere on the graph. We start tracing the curve, and then we get to the 3, and we see what happens. And if you look at that, we're at some value there. And if I look at my, my function, let me write it up here, which is my simplified function, 3x plus 1 over x plus 3. And if I were to substitute 3 into that, I would get 10 over 6, which would be 5 halves. 5 thirds. I'm dividing by 2. 5 thirds. Okay? So as x approaches 3 from the left, not that I can actually land there, but the idea is I'm approaching there. So f of x is approaching 5 thirds. So we would write the limit as x approaches +3 from the left-hand side, so we put a negative in the upper left-hand corner, of f of x is going to equal 5 thirds. Understand that the value of the limit and the value of the function don't always have to be exactly the same. Okay, and then finally our last two, we're doing the limit as x approaches -3 from the left of the graph of f of x. So this time we're coming from the left-hand side over here, and we're approaching -3 along the curve, and we see the values keep getting bigger and bigger and bigger. So they're approaching infinity. They're unbounded. So we would say the limit as x approaches -3 from the left, so we put a little negative sign up there, of f of x is going to equal infinity. And doing the same with the other side of +3. So now we're coming from the right, so we're going to start all the way out here. We're going to trace the curve until we get to +3 on the x. And we can see we're approaching that same value we did from the left, which is 5 thirds. So we'd say the limit as x approaches 3 from the right of f of x equals 5 thirds. So that's the difference between the way we kind of wrote the notation in pre-calculus and the way we're going to write it now. Okay. So I want you guys to answer this part. Can you explain what the value of the limit represents in terms of the graph? And then we'll discuss it tomorrow in class. Okay? So informally, a limit is a y value which the function approaches as x approaches some value. And we use this notation, the limit as x approaches c of f of x is L. We want to make sure that we understand that L is a real number. That's important. For the limit to exist, it has to be a real number. Okay, so let's estimate some limits from the graph. So consider the function shown at right. You want to find the limit as x approaches 4 from the right. The positive sign tells you it's the right-hand limit. So if you want to think of the function as a highway, as I was showing you in the last example, it says from the right, not to the right. So that means you're headed towards 4, but you started off to the right somewhere. So what you want to do is stop at the vertical line, x equals 4. The y value you stop at is 3. So the limit as x approaches 4 from the right is 3. So let's go through and do these together here. Make sure I get the picture and everything in here. Okay, so the value of f of 2. So you're just going to the function and finding what the value of the function is at 2. And it would be right here. So the value is -1. Okay, so then we have f of -1. So same thing, we're going to go to where x is -1 in a graph, and we're going to find where the function is defined. And that is defined at 4. Right up there, that circle right there. Okay, so part C now asks the limit as x approaches 4 from the left. So I want to trace my highway, so to speak, towards 4 from the left. So here's along the curve. I'm coming from the left, and so I approach and end up at 3. Okay, then 2 from the right. So I want to approach 2 from the right. So from the right-hand side, I'm going to trace the curve down here, and I end up close to the value of 1. Okay, 2 from the left for letter E is now I'm going to trace the left side of the curve as I approach 2, and I end up right there at -1. The next one is I want to approach -1 from the right. So I'm going to start on this side, trace the function as I head towards the right side, and I end up right there at 2. So then I'm going to go from -1 from the left. So I'm going to come this way from the left to -1, and I see I approach the same value of 2. Now I'm doing next -4 from the right-hand side. So I come from the right towards -4, and I end up at 2. Next, -4 from the left. So I have to trace the curve from the left-hand side of -4. But what you notice here is the curve stops. So I can't trace it. So this limit does not exist. We usually just use DNE. Okay, so now let's do just the limit of -1. Okay. So what I want to notice is I did -1 is right here, and if you come from the left and the right, you approach the same value. That means the limit exists, so we get a 2 here. All right, now we're looking at the limit of 2. Now here's where we have a bit of a problem. If we look at our right and left-hand limits that we did earlier, if we look at 2 from the left, we got this, and 2 from the right, we got this. Those values are not the same, so this limit does not exist. They have to meet at the same point. And what we have here is we have that jump there. So we don't have a limit because there's 2 different values. The limit as x approaches 5. So we can just see where we're at 5 here. This continues. So in both directions, we end up at that point. So we're at -2. The limit at 0, same thing. If we look coming from the left and the right, we end up right there at the same point. So that value is -1. And so the value at 1, the same idea. We're going to approach 1 from the left and from the right, and we're here at -2. We're going to pick up the rest of our discussion of limits in our next video.